Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host, Shafu, and today's guest is Pascal. Pascal, thanks for taking the time, man.
Yeah, thanks for the invitation. I'm looking forward to present the stuff I built.
Yeah, for sure, dude. Pascal wrote this new Oracle design, which is called Scribe. So really looking forward to jump into the code. Pascal, why don't you briefly introduce yourself, introduce the project, and then we can directly jump into it.
Yeah, sure. So hi everyone, I'm Pascal, or merkleplant, better known. I work for Chronicle Labs. We are currently powering MakerDAO. We are the oracles for MakerDAO, and soon we are also expanding to be open for other oracles. And yeah, so I developed the Scribe project, which is called an efficient Schnorr multi-signature based oracle. And yeah, let's jump right into it, or better, before we jump right into it, let's maybe check out the old version, the one from MakerDAO, which is the median contract. It's under MakerDAO median. And my job basically was to optimize this contract, to build a new architecture so that we can update the prices more often and generally save a lot on gas fees, because these oracles, as you all know, need to be updated, or poking as we call it, need to be poked a lot of times so that you always have a price as fresh as possible. And yeah, if we check here into the contract, we see, just scrolling quickly through it, it's really not long. It's like 170 lines of code. And there's basically just one function that's really important. We have here the value of the oracle and a corresponding age field. This is together the value from the oracle that you can read, and the age of the oracle value. And the really important function, which kind of the whole thing is centered about, is the so-called poke function. This is called by, as you can see here, it does not have any modifier. There's no message.sender check, so it can actually be called by everyone. Everyone can update the oracle whenever they want. And yeah, this updates in the end the value from the oracle, and also then of course the age of the value. And afterwards, everyone has a fresh price. And if we just look into this function, there, like from a performance point of view, there are two things that are that you maybe see directly. So first of all, we have here a set of arguments, which are all arrays. And we see here that we have here some VRS arguments. So this is some ECDSA signature, and we have the value and the age for the which are signed by the data. And we see here that the call data is basically linear increasing the more secure we want to become. So we have here the so-called bar parameter, which defines how many of our whitelisted feeds, so the servers that are allowed to, or the addresses that are allowed to push to the oracle, which we consider as trustworthy, we need to have some kind of consensus of how many we need. So for example, we can have 20 feeds whitelisted, and we say we need 13 of them to agree on one price. And then we assume, okay, this price is correct and this is secure. And this require statement here says that we expect bar many values, and therefore also bar many signatures and ages. And what we see here is, if we want to increase our security parameter, if we want to say instead of just 13 servers, we now want to have 50 servers that need to sign every value. So we want to become more secure. Our call data load is increasing linearly as well. So we have a call data of O of number of feeds. And this is still fine if you think about like layer 1, where call data is not the most expensive part, but especially on layer 2, it's getting more and more tricky, because for the current median version, more than 95% of the cost to execute this poke is just this call data. So one question that we had was, how can we constrain this linear call data grow to sublinear, or even better, constant? This would of course be the goal. And then we see the whole other block of the function is a for loop. And we see here that we iterate over each element. So this also means that we do not only have a linear call data load, we also have a runtime, which is linear to our security parameter bar. And this is also something that we would like to optimize. Can we maybe make it constant in some way, or at least a little bit lower than linear on the average case. And yeah, the rest of the stuff here is basically pretty simple, and also what we will continue in using Scribe. So we cover for each value and each age via the signature, the signer, check that the signer is actually an oracle that we trust. So someone that we whitelisted and is allowed to give us new prices. And then just some sanity checks, like the age, of course, needs to be newer than our current value's age, and some uniqueness checks so that we don't run into double signing attacks. And yeah, then we basically already also set the value already. And yeah, this was the goal, to optimize. So how do we make this in generally more constant, or at least less linear?
Interesting, Pascal. Yeah, I think from a general point of view, I think you develop an intuition pretty quickly when you write smart contracts that for loops are really bad. So when you see a for loop, that's a really good place to start thinking about, okay, how could I do this in another way?
Yeah,
So
exactly. Even worse if you see something like while true, and then you check, okay, where's the break? Where's the break? But yeah, this is already something you would like to not have. Yeah, and so how can you, how is our architecture basically, just to point this out, is we have a peer-to-peer network of all the feeds. Feeds are currently actors who are considerably invested into the Ethereum ecosystem, for example, Etherscan, MakerDAO, Gnosis DAO, the Gnosis project, and they all have servers set up. They all fetch prices from different exchanges or other data sources. They sign them and exchange them in the peer-to-peer network. And this is all open. Everyone can listen to them. And as soon as if you listen to this peer-to-peer network, you can collect these values and ages which are signed. And as soon as you have bar many of them, you can be the one who pokes the oracle. So we, like actually, for example, if a project wants to increase the number of pokes, wants to increase the number of updates for the oracle, they can just themselves listen to the peer-to-peer network and poke it themselves. There's no reason why we should not allow this. We have all the verification of this data inside of the signatures. So the message.sender doesn't matter. But okay, let's go now to the cool new stuff, which is Scribe. So just yesterday, we released the first version. It's really hot out of the press. And yeah, as I said already, it's an efficient Schnorr multi-signature based oracle. And first, maybe the question, what is a multi-signature or an aggregated signature? It basically means that for ECDSA, if you sign one time, then that's your signature. You can recover one signer. But there actually exists multi-signatures, which makes it possible that not just one private key is signing the data, but a set of public keys together. You can imagine it, and this is not that wrong, but there's a bit more math tricks involved. You can kind of imagine it as just adding up all of the signatures together. And this way, then you have the sum of all the signatures is one signature again. And then kind of in the verification, you can add all these public keys together and then check whether this maps to the signature. There are a few more issues to do this, but that's the general idea. And yeah, it's you see here it's based on Forge. We have unfortunately we have some JavaScript dependency because we use some kind of vector-based tests for something. But yeah, generally we use a lot of as I hope like a lot of best practices in Forge. One, for example, is that all of our dependencies, this is a general rule that we use that we took over from Maker, which never used or really, really rarely used any kind of inheritance or importing code. They always copied code from A to B. And then it was really easy to see if you always copy the same 10 lines of code, it's hard to make a mistake there. We decided that we want to use some kind of importing, but we want to have dependable builds as much as possible. So if we, for example, update this library here, and Shafu, you're going to clone the repo in a year, and we updated the library, you should not end up with a different code, because this would mean maybe we make a mistake in this library, and then we have a mistake in Scribe. So this is why we version all the dependencies. One thing also to point out is that that Scribe itself will not be open source, or is not open source, it's source available. So the Scribe code itself is under a business license. But what's interesting, I hope, and what should advance the general EVM space is that this whole Schnorr signature stuff is everything open source. So basically everything that's not directly business related to us, we put under an MIT license, and just the really specific business code is under a business license, which will become MIT in 3 years, I think. And yeah, so let's maybe check first into benchmarks to set the stage and see what we managed to achieve. So we see here we have this bar parameter, which says how many fields need to sign the data so that we accept the value as the new canonical value of the oracle. And we see here that the poke function, well, it increases linearly, which is understandable if we check into the code, but it's fine. So for example, currently we have most of the time 13 out of 20 fields need to sign data. So one poke will be around 130K of gas. But we also have a different flavor, which is called Scribe optimistic. We'll come to that in a second, but optimistic basically here means that we first optimistically assume the price is correct, and then have an on-chain fault mechanism where everyone can challenge this optimistic value and can say, no, this value is actually wrong. We will check this on-chain, and if it's wrong, then the feed who pushed it will be kicked, and yeah, we will not, of course, not use that value. And we see here that we have a linear increase still in the runtime of Scribe, but for Scribe optimistic, we are basically constant. So this is very important from a business perspective for us, that we can increase the security of our oracles without increasing the cost of updating it, because at some point we would need to transfer this cost to the user, and users, like, they're not the experts in oracles, so maybe they say something like, we don't need more security, it's fine, we don't want to pay more. So it's kind of puts us into a tricky situation. But with Scribe optimistic, we actually managed to stay constant for updating the oracle. And then let's a little bit set the stage for Schnorr signatures, because it's probably something that is not well that probably not many people know about. So Schnorr signatures is not very much used in the Ethereum space, or actually I think we are the first one who will use them on a production scale. They are, however, very well known in the Bitcoin space. There's the BIP 340 standard proposal, and this allows multi-signatures for Bitcoin wallets. In the Ethereum space, we so far always used either multiple ECDSA signatures, or we went to BLS signatures. And BLS signatures, we did a lot of benchmarking there. They are quite expensive. You have to do quite a lot of precompile calls, and for BLS precompiles, we do not have a recover, kind of an EC recover call. You have to do a lot of the computation inside of Solidity. And yeah, this may be tricky. So we basically looked at BIP 340 and tried to, okay, how can we take this Schnorr signatures, put them on Ethereum, and what kind of problems arise there. And I'm not going to go now through all of this math stuff, but it's quite interesting. Like, check it out if you want to. We use one very interesting trick from Vitalik, which he posted in 2018, in that you can actually use an EC recover to do an elliptic curve multiplication. This allows us to verify the Schnorr signatures, otherwise it would be impossible. And then there's the very hard problem, which I also think is the reason that no one used it yet, the key aggregation for the Schnorr signatures. So as I mentioned already, for multi-signatures, you can imagine it this way, that we add all of the single signatures together and get one sum of the single signatures. And this is then the aggregated signature. But this adding public keys together, this is in the end elliptic curve addition. And this is, so far it was always very expensive to do on chain, and no one actually did it. And this is why aggregated keys have the problem, like why you could not compute them on chain, because it was not optimized again. And then you maybe ask, okay, but why can you not push all the possible aggregated keys already on chain before you launch, like before you verify? So for example, if we have 13 fields, why do we not push all possible sums of their public keys on chain already? And the reason there is that we have exponential growing, like an exponential runtime. So if we, for example, have 13 fields with like a bar of 13, we want 13 fields to always sign, and 20 fields in total, then we have 13 out of 20, which is like 75K. So for this single setup, we would need to store 75K of public keys on chain. And this is, of course, like by far not manageable. So we came up with a simple key aggregation algorithm, which is actually really simple. It's just adding all of this together. It has some vulnerabilities though, and this vulnerabilities was kind of took a lot of effort to make sure that these vulnerabilities are not possible in our case, or that we verify that we prevent them. But yeah, I promise to not go too much into the math. So if you want to check it out, it's very interesting, and there will be more posts coming about it. And let's now jump into the IDE to check more into the code. So if we see here, we have the source, like everything is normal Foundry, Forge layout. There's nothing special here. We have our source directory. We see there's yet not so much. We have the Scribe and the Scribe Optimistic and the corresponding interfaces. And we have a few libraries, basically the Schnorr library, which does the verification. We have some SCCP-256K1, which I from now on I think just call K1 because it really breaks your tongue. This is the elliptic curve that Ethereum and also Bitcoin is based on, and we need to do some computation there. And these are just two small helper libraries that we won't go too much into detail because they're also not that interesting. But yeah, as you see here, all of this code here, so the Schnorr verification code, for example, this is all MIT licensed, it's open source, play around with it. You should be able with this library to quickly implement Schnorr multi-signatures in your system and not have to refuge to BLS or the linear increase of ECDSA signatures. Before we jump into this on-chain code, I would like to go into the script directory. So what we put a lot of focus on is basically me and my colleague, we started to develop this Schnorr scheme and started to experiment and did a lot of proof of concept and stuff. And we quickly found out, okay, we have a lot better understanding about this than all the rest of the team, and especially the backend developers, because they didn't work on that. So one thing that we put a lot of focus on is to, let's open this here. Yeah, is to do the signing and basically the whole backend part that's running inside of the backend code, inside of our P2P network, to implement this inside of Solidity as well. This gave us two very strong positive sides. First of all, we've kind of had a documentation, like an actual running documentation of how the backend should implement the signing mechanism and also some other parts. And it gave us a very nice ability to later fuzzing test between the backend and our own Solidity code. So we were able to, when the backend started to create like the code to to do this multi-signatures, we were able to do the same on Solidity and always check whether we produce the same signatures or not. So this is a tip that I would like to point out. Try to write your backend code into Solidity as much as possible and have it as a living documentation. It also helps you a lot with calling your own contract a lot and redefining the interfaces and making the whole workflow for specific transactions better. And
this is really interesting. This is really interesting, Pascal. So you're basically talking about backend stuff which was probably written in JavaScript or Python or something. And the problem is the backend or Go or something. The problem is the backend developer doesn't really understand the signature stuff. So basically, this is like a reference for the backend dev to make sure, okay, I'm getting the same result.
Exactly, it's a reference, and it's also continuous, like we can use differential fuzzing. So we basically call their libraries, which they use for signing, and we call the Solidity code and check whether they produce the same signatures. So whenever they make updates in the future, we can directly run our test suite again, and if they introduce a bug, we will directly notice it. Nice. Exactly. And here, for example, we have like our backend code is called Oracle Suite. This is also where the stuff is implemented. And here we have a library to call this backend code with we given a set of private keys and a message and expect a signature back, a Schnorr signature. And this library here then returns us the signature, and we check it, first of all, whether Scribe can verify the signature. And then we also check whether our Solidity code would have produced the exact same signature. So we also make sure that we have deterministic signatures on every level. And then let's maybe jump more into the code, quick check into the interface. Okay, so we have three structs, three types basically. One is the poke data. This just encapsulates the value and the age. Then we have the Schnorr data. Schnorr data, like a Schnorr signature, is not just the signature. It's also there's also the commitment, which is part of the signature. So we encapsulated both of this. And the signer blob is just a blob of bytes, and it tells Scribe which fields participated in the signature. And then we have the ECDSA signature. We just encapsulated it. So we see here already that the Schnorr data seems to be constant, and ECDSA data, we won't use lists of ECDSA data. So we are nearly totally constant in every update and every poking that we do. We use a lot of, we use extensively every kind of NetSpec, of course, to have better documentation, and also on Etherscan and stuff, when normal users or the not so technical people in the team need to check something, they can see it on Etherscan easily. And we also provide some kind of Chainlink compatibility for projects who are using Chainlink, but cannot update the code anymore. Maybe we can just update the address. So we provide some functions from Chainlink, and also make sure that the common integrity checks that you hopefully do, like check the answer, that it's not overflowing, check that it was updated at least X amount, at most X minutes ago or something like this. All of these checks will pass if you have the normal integrity checks there. And then let's go into the Scribe contract. Let's maybe first check out the poke function. So we see here we have two different poke functions. One is the normal poke, which is defined via the interface, and one which is optimized for the function selector, so that we have a lot of zeros inside of the function selector. This means like we save, I think something like 12 gas per byte per call. So in this case, we have 3 0 bytes. So this is like 30 gas that we save. My tip is to not put this into the interface itself, because you maybe want to change this in the future. Just have it for the people who understand the code well enough and who are quick to update. They can use this kind of code, but always have the normal function there, and do not depend on this function via the interface. Don't make promises that they stay. And then we have here the poke function, which is, let's check it out. So what are the arguments again? We have poke data and Schnorr data. So the signature that signs that this poke data is correct. And we see here, okay, this is constant. That's cool. So we managed to get from linear call data load to constant call data load. And this is especially important for layer 2s. And then we see here that we do 2 simple checks, and we verify the signature. And so far, it does not look like any linear runtime. Like this is all just constant runtime. And if the signature is okay, then we set the value correctly. And if it's not okay, then it will return an error, and we revert with the error. So nothing too unexpected here. And so far, we seem to hold our optimization promises. And then let's get into the big function. I'm going to make it a little bit smaller, just to have one time just to see it one time better, the whole scope. So this is the verify Schnorr signature function. And we see here that it is comparably long. We were thinking about whether we should outsource some of this complexity into single functions, but the problem is it's basically just one algorithm, and you cannot really divide this algorithm in different parts with specific meaning. You could have something like called first half of the algorithm and the second half, but that does not really bring anything for complexity. So we decided to just go with a little bit longer function. We first set a set of variables. The variables here are basically some kind of who's the current signer. So this is the current signer public key. We need to, if we get the Schnorr data, we need to verify that the signature is correct. And for this, we need to have the aggregated public key, because the aggregated public key is the sum of all public keys that signed the data. And this should map to if you sum all the signatures together. So we need to compute all of these public keys together, and these are the variables holding the important data for this. And then we have this aggregated public key variable, which is the current sum of the data. We see that we check, this is the same check as if we go back to the median. We see here we did the check that bar needs to be reached. It needs to be equal to bar. We do the same here. If it's not reached, then we return. One question you may have is, why do we expect here exact equality? So for example, if we want to have 13 feeds to sign the data, why are we not fine if 14 or 15 or 16 sign the data? And this is because, like as we all learned in current times, EVM compatibility is not really like one specific thing. It's more like a spectrum. Like some chains are more EVM compatible, some do not implement this kind of feature or take longer. We see this currently with the push zero problematic, and also with the EVM chains that have here and there some kind of problems. And this basically allows us that we have always the same amount of gas that we use. So we do not run into block gas issues, because you could, for example, what if we have 100 feeds lifted and you provide us with a signature of 100 feeds? Then maybe we have an EVM chain which has fast blocks but small blocks, and we would reach the gas limit of this. And you cannot, we cannot update the oracle with this set of signatures. So we basically said, okay, let's constrain it, and then we have one constant round of signatures of one time, and cannot run into any issues there. Afterwards, we load the public key from the storage. We do this in unsafe manner. Let's maybe jump into this function, which is the first assembly, I guess. So we have an array of public keys, and this stores the public keys, which is an X and a Y coordinate. And we load the stuff here in unsafe manner, which means we do not do any index out of bounds checks. We directly just load the elements. And if you know about the storage layout from arrays, it means that basically the storage slot, you have the storage slot where you define the array, and from this you take the hash, and this is then where the elements are actually stored. And because we have such a basically infinite space of storage, we can safely assume that everything behind this array will be zero. So there will nothing be written to it. And if we have this invariant, which we define as invariant and which we keep, is that the 0 point is never being able to be lifted, and it's never can never produce valid signatures, then we can just say, okay, forget any index out of bounds checks. We just load the element directly. If it does not exist, then we load 0 from the storage, and this will be cached at a later point. And why did we do this? What's the idea behind this is, if you would not do this, then you would need to have here some kind of check if pubkeys at the point index pubkeys.length is less than index, then revert with something like index out of bounds. And if not, then we can load the array element. But this means that we always have to pay gas, like this if statement. We always need to pay gas for every happy case. And for the unhappy case in which we are really out of bounds, we would revert quite early. And we decided in a lot of situations here where we coded that we always want to optimize as much as possible for the happy case, because this is what happens 99.9% of the time. And if someone really calls us with an invalid index for this public key, then we revert at a later stage, and he will pay more gas, but he was the one who made a mistake. So it's his fault. And it was like probably not our backend, at least we hope so. Then one thing that you see throughout the code a lot, which we pay a lot of attention, is having assert statements for basically everything. As soon as you think that something is true inside of the code, start to write an assert statement and keep it there, and have it always activated during testing, and make sure that you're unable to ever catch like this assert statement. This helps a lot with auditing, because auditors or security reviewers realize, okay, like this was his assumption, and they can better follow your pattern of thinking. And it also helps a lot with formal verification if you use tools like HEVM or other symbolic execution environments. They mostly are built on assert statements. So keep them inside of the code, just uncomment them before you go online, before you push them on chain, because it costs unnecessary gas later on. And then if we have the signer pub key, we if we have the public key from each signer, then we transform it into a different representation. We'll come to that in a second. This is like elliptic curve stuff, the different ways how you can define elliptic curve points. And then we have here, unfortunately, a loop, which is again bounded by bars. So we have some linear runtime again. And this linear runtime is there because we need to add all the public keys together. And for this, we need to iterate over everything. And this we just do. We make here sure that we have that every signer is strictly monotonically increasing the address, just to make sure that we don't have any double signing. And this is also nice because it enforces some strict ordering for the backend. So the backend is not allowed to give us the set of signers in every kind of order. They have one specific order that they need to give us, and it generally helps with debugging everything. And afterwards we verify the signature, and if it's okay, we return 0, return true. Fine.
Yeah, Pascal, could you go into more detail? So I understand that, okay, you check that it's not the same address twice, but why monotonically increasing? That's it.
So if we have, if we would just say that this is, so if we would just say that it needs to be, so this was the last signer, the signer that we had before, and this is the current signer. And we always look back that our current signer is, as the address is bigger, has a higher number than the signer before. And if you would not have this, you could have some double signing attack again, because you could say, you could have the same signer twice. And this would be, of course, very bad. This is basically similar to what MakerDAO did here before. They used a Bloom filter for that, and also checked that each oracle, each feed only signs 1. And this is why we have here the do not it needs to be strictly bigger and not just bigger or equal.
Okay, so it's the only reason is to check for double signing.
Yeah, but it has the nice effect that this is the only reason why it has to be there, why it must be there. But it also gives you the nice effect that you have to encode the signers always in the same order. So if the backend would be allowed to give you different Schnorr signatures, like the same Schnorr signature, but with different encoded signers, it could, it gives the backend some more freedom in how it calls the contract. And generally as a contract, I think we should be as strict as possible in what we accept at all, and make sure that for every Schnorr data, so for the signature and this encoding of the signers, there's only one possible representation. It just generally constrains the whole system more to do it exactly as we want it, and no other way is allowed. And then we have here the verify signature function, and if the signature is okay for the message, then everything is fine. And if we check out the poke function, then we see if everything is okay, we don't revert, we set the value, and everything is done. And this is basically how Scribe works. And then we implemented one other flavor, because as you noticed already, we have here again some linear runtime. So if we would increase bar, our gas costs would increase. We don't want this, we want to be constant. This is why we implemented an optimistic version called Scribe Optimistic. One difference between other optimistic oracles, or generally optimistic, it's kind of an overloaded term, is we actually have on-chain fault resolution. So there's nothing like you have voting, or people can vote against this value. or something like this, we have here an OP challenge function, which challenges a current optimistic poke. And everyone, as you can see here, it has again no modifier, it has no message.sender check. So everyone can check out our oracles, check out optimistic pokes. And if you think that this poke is wrong, you can call the optimistic challenge. And okay, wanted to come to this later, but this may be interesting for MEV searchers. If you challenge an invalid optimistic poke, we pay you some ETH. This way, we want to make sure that other people are incentivized to check our oracles, and yeah, they get paid ETH if the optimistic poke was actually wrong. And this also gives projects that integrate us more possibilities to monitor to make sure that they only have valid values. So with other oracles provider, you can monitor the oracle and you see, oh, there's an invalid value. Someone fucked up there. What do you do? Well, you can basically shut down your protocol or pause your protocol or something because you know that it has an invalid value. In our case, you can be yourself, like you can say, oh, this is invalid. Okay, I call this function. I make sure this value never advances. So we can give some response, like we can give the users responsibility to check that our values are correct. And how does this optimistic poke work?
Okay, maybe one thing, Pascal, the ETH is just self-funded, or where does it come from, the reward?
Yeah, so currently, like we can, first of all, it does not need to be ETH. So this is optional that we want to like add. Everyone we have a normal receive functionality. So everyone can send ETH to it and we will pay it out to the next one. We will do this for our important oracles, but it may also be done by our customers. If you, for example, are a customer and you depend on our oracle to be correct, then you can send some ETH into it and make sure that more people are incentivized to check our oracle and have, again, higher guarantees. So generally, our whole mantra, our whole philosophy at Chronicle Labs is you should not trust us. You should not trust us in any way. Every single step should be verifiable. We do not have here any voting mechanism. We do not have anything where you need to trust us or where you cannot step in yourself. If you don't trust us to update the oracles on time, listen to the peer-to-peer network and poke yourself. If you don't trust us that we optimistically poke the oracle correctly, set up a simple script. You just have to listen to 2 events and make sure about it yourself. And you even get paid for this. And this is basically inside of our whole organization structure that we even in the peer-to-peer network already, we will provide functionality for people to verify every signature that's running through the peer-to-peer network so that you can even not just verify the on-chain stuff, but also verify the peer-to-peer stuff. And yeah, if we go into the optimistic poke function, we see again, we have here an optimized version, this time with only zeros. So we again save a little bit of gas. And then we have the actual function here. And here we see again, we have constant call data. This is perfect for, doesn't matter if layer 1 or layer 2, call data is always expensive. And we see here that if we scroll through it, that there's not a single loop. So there, an if statement, some hashes is being executed, but not a single loop. So everything inside of this optimistic poke is constant. And This is the reason why we will use Scribe optimistic for layer 1 for Ethereum, and Scribe itself we will use for basically everything that's not Ethereum mainnet, because we have there already constant call data, so we cannot get cheaper than that, and the execution gas does not matter anymore on optimistic rollups or generally any kind of rollups. So the optimistic Scribe, it's a little bit of a twitch because we use the optimistic oracle on the non-optimistic chains. On the optimistic rollups, we use the non-optimistic version. Yeah, it's I'm not a marketing person. I was the one who named this. So yeah, but yeah. So what how is this working? So we have, of course, some kind of challenge period. This challenge period, we're not yet sure which values we will use there. In the beginning, it will be like a higher value, and then over time we want to lower it depending on how many people we see are running this kind of MEV searcher bots, or how generally secure, confident we become into the system. But we have some optimistic challenge period, which during which you can always challenge this value. And if you did not challenge it, or no one challenged it during the time, then we finalize the value.
Okay.
And yeah, we have here the same checks. So we check that the poke data is not stale, and also that it's not from the future. This would be just, it does not need to be here, but it could just get a little bit dirty if some fields have their clock, their internal, like the operating system's time wrongly configured or something, then we could run into problems that we get data from the future, and this would just generally be hard to debug, and every monitoring system would alert us. So we prevent this case altogether. And then, of course, we need to be able to not be DDoSed in this case, or just DOSed. Because if you optimistically poke something, and we have the challenge period of, say, half an hour, it means we cannot optimistically poke again. There's only one optimistic poke currently possible per time, and someone could just continuously send invalid optimistic pokes, and we could still poke. The poke always overrides everything, so we don't have to depend on this optimistic stuff, but you could basically make sure that all our optimization savings are gone via just optimistically poking invalid data. So we need to, in case this data is invalid, we need to punish someone, we need to kick someone, and this someone is the feeds, which are the like trusted actors in the system, in the space. So if we want to optimistically poke, we have the poke data and the schnorr data, which is signed by like 13 different feeds. And then you sign both of this data, again, you sign via a normal ECDSA signature. And this is ECDSA signature must come, if we check here, we do here the EC recover, and we check here, it must be a feed. And if it's not a feed, then we revert. So this optimistic data needs to be signed by, this poke data needs to be signed by a feed. And then we store the feed and the schnorr data to that, or commitment to that, but basically the feed. And if someone challenges our optimistic poke, and yeah, it was successful, then we can prove, then we have proven, or the caller has proven, that the feed did its job wrong, and we kick the feed. So this allows us to not being DOSable. But even if someone would find out a way to DOS the system, or even if we would find now a bug inside of the optimistic Oracle part of the optimistic code, Scribe optimistic itself is Scribe. So we just extend the functionality of Scribe. This also means that we still have the normal poke function. So even if this optimistic mechanism is in some way broken in the future, we do not lose everything. We basically don't lose anything, just our gas optimization. We can just continue with normal poking and always verify the schnorr data directly on chain. We are not sure whether I mentioned it. So the optimization, of course, happens here because we don't verify the schnorr data on chain. We just verify the ECDSA data, and the schnorr data is just verified in case someone challenges. And yeah, this is basically how Scribe and Scribe Optimistic work. And this code is under the business license. So this is our business specific code, but the code where we spend the most time, and where it's also, which I think advances the space in general the most, is this open source code here, the schnorr signature verification and the SSCP K1 elliptic curve stuff. And if we go into the libschnorr function, we see, just going out a little bit once, we see it's one function with a lot of comments, but actually not so much stuff that's happening, and it's just one function. It's just the verify signature function. And yeah, what's happening here exactly is not so interesting because it's a lot of math. But what I would like to point out is that we use a lot of checks here, which are not necessary from Scribe's point of view, because Scribe already makes sure that these conditions can never happen. But after we optimize the code a lot, and we're still a lot cheaper than we anticipated to, we added additional checks, which enable us to have a defensive mechanism. And any questions so far, or should I
Yeah,
go a little bit
question.
slow or something?
Why not create an own library for the Schnorr stuff? Like its own repository or something.
Yeah. So yeah, this was also a question whether we should do this or not. And initially we didn't want to do this because we had this and some other checks missing. For example, here we can have this check make sure that there's no signature malleability, which you all know from ECDSA. But in Scribe itself, we already make sure at a higher level that we never run into signature malleability issues. So we initially didn't have this checks and didn't want to therefore publish a library which would be, like, for most use cases vulnerable. And this checks we just activated after the second security review, after the second audit, and that was already too much integrated into the whole system. But yeah, basically, if you want to, though, we have the libschnorr library and we have the libschnorr extended library. Here is the signing also implemented, the signing for a single private key or for multiple private keys. And you're free to use them or also set up a repository for that. Just make sure that you also have the Schnorr specification correctly included or generally included, because otherwise it just looks like magic numbers which no one understands. I mean, it does anyway, kind of, but yeah. And then for the elliptic curve stuff, this is important that this library is not an own project in itself, because it's not a general elliptic curve library. Like, there's some stuff that you normally do in elliptic curve libraries, or provide at least, which we don't do here because we wrote this specifically for our Schnorr signature library. So if you copy this code, if you use this code, make sure that all your assumptions are correct, and that you either use it for Schnorr signature stuff or check it against other famous libraries to make sure that no invariant is broken. Here we also use a lot of times like assembly, or even, I mean, I'm not sure whether that's worse or better, but also some bit manipulation stuff, so optimizations on the bit level, just because these functions are executed a lot of times during the whole process, and this is where we wanted to be as optimized as possible. And what we consider as our or what was for us the breakthrough in being able to do this on chain, which opens up new doors to multi-signatures, is basically that we found this one. Let me copy this. That we found this one elliptic curve edition, which looks very weird, and you don't understand it, I guess. I don't really understand it, but I implemented it. It's from this website where a lot of elliptic curve computations are defined and written how it's optimized. And one thing that's important here, or make it a bit bigger, one thing that you have to look out if you search for like computations that you may want to use is the assumptions here. And this has an interesting assumption that set2, what it is we come in a moment to, equals 1. And this library, this computation allowed us to do this public key addition on-chain in an efficient enough manner, because normally most contracts use this library, this code here, and this code has the assumption that both of them are 1, which makes the whole process like 1,000 times more gas expensive. And the reason for that is that there are basically most of the time two ways how you can represent points on elliptic curves. And this is our public keys. The one is the so-called affine point, which is just the normal one. It's an X and Y coordinate. So if we have a coordinate system, we say, okay, it's at X point there and Y point there. So we have defined the exact point. And this, for example, is how the Ethereum address is defined. So we take from this point, we ABI encode this together and take the hash of this. And this is the Ethereum address. So it's very important that we basically have this point as this representation is our standard point. But then there's also the so-called Jacobian coordinates or Jacobian point. And this has another field. It's a set point. It's based on basically angles of how you can reach the point in the coordinate system. And what's as a rule of thumb is that you do all computation always in Jacobian points and then transfer back to affine points once you have the result. And if we look here into how we can get from an affine point to a Jacobian point, we see that's constant. We just use the same coordinates and set the set coordinate to 1. But if we want to get from a Jacobian point to an affine point, it's a little bit more complicated. And especially we need to compute some modular inverse. If we go into the modular inverse function, we see, shit, that's again a loop. So here's the solidity code. So we have again a loop in our whole system, which is the whole reason why we started. Like we don't want to have any loop. We want to be as constant as possible. This loop you do not get around in total, but what allowed us to use the other addition formula instead of the general one is that we have to use this loop. We have to run through this loop only once. This loop is generally implemented like this in every Solidity library that I found. So if we just check into it, like we see here, okay, as long as x is unequal to 0, we divide some number by x. And okay, as an optimizer, you directly see the Solidity compiler add some division by 0 protection. Even though in this case, it's like very obvious that we don't need it. So the first idea is, okay, then do everything inside of this in an unchecked block. But if you then benchmark again, you notice, okay, unchecked blocks actually do not remove the 0 protection. They only remove over-under protections. So to get rid of this division by 0 check, you need to go down to assembly. There's no other way.
Oh, that's interesting. Unchecked doesn't remove the division by 0?
No, unchecked doesn't remove division by 0.
Oh, I didn't know that. Okay.
You could maybe call it unfortunate, but on the other side, like to have a division by 0 would be really bad. So it's I generally like it. The more security guarantees the compiler gives you, the better, because if you are sure that you don't get division by 0, you should prove it. So in this case, we wrote here everything in assembly, which means we also don't have for the subtraction and multiplication, and this subtraction here any kind of checks. And what we did is define why all of these cases, where all of these computations cannot over or underflow. Or in the division case, it's obvious. But we also defined here, because we have a division, which means an integer that we round down if we have a result. And only because of this rounding down, we are able to prove that this cannot overflow. So if you jump into assembly because of unchecked, because you want to do not have this checked, make sure that every single computation is proven, that you prove every single computation of those cannot underflow or have a division of 0. We generally do this throughout the whole code. As soon as we have unchecked, we have a comment above and explaining why each of the computations that are normally checked cannot run into problems. And this is also part of the highly optimized code, as you probably see. So this is this addition formula that I showed before, which we then further optimized a little bit for the EVM. And here, for example, we don't need anything checked because everything is inside of this modulo P, which means as soon as you have basically an overflow inside of a modulo computation, you just start at 0 again. You have this clockwise computation. So overflow is kind of like inside of the modulo, you want to have the overflow. That's part of the cryptography, which makes the computing it backwards so difficult, or like that difficult that we assume it's secure enough to manage billions of dollars. But we do not need any kind of UN 256-bit overflow protection, because everything here is modulo P, so we know everything is always less than P, so we know there can never be an overflow. And yeah, this is what you also like. What we use a lot is at custom annotations for code. So if you think about this Scribe optimistic and the optimistic poke, let's imagine I'm going to optimistically poke an invalid data, and someone wants to challenge this. The very most important thing during this challenge period, and this is also what the big problems of the rollups is, you need to prove that it can never revert or run into out of gas issues. Because if I would be able to make an invalid poke and you challenge it, and this challenge function would revert, well, that's it, right? The optimistic poke at some points become valid and the system is hacked. So we have a lot of times for every function that's being called in the challenge function, we have an invariant that it does not revert and uses a non-infinite amount of gas. So in this case, even a constant amount of gas, or at least the loop terminates at some point. And for this loop, if someone wants to check it, this is the extended Euclidean algorithm. This loop is also proven mathematically to end in some finite amount of time. So every single step here like is proven that it cannot run into out of gas issues. And we tested it, I hope, sufficiently enough to also prove that it cannot revert. So the challenge period should always work out. Then one thing that I would like to generally start a discussion about in the whole community, because the first time I saw it was in OpenSea repository, where they generally used the highly optimized assembly version of, what was it? OpenSea is the project, but what was the repo again? The repo name?
Seaport?
Seaport, exactly, yeah. Which is like this ultra super optimized assembly code base. And they wrote a reference implementation for that in Solidity, which is not optimized at all. And I really like this idea, and I think this is the only way that we should approach optimizations. Otherwise, it's just too damn dangerous. But this also means that our testing should not be built on one contract anymore. It means that our testing should be mostly built on the interfaces, because you then want to check, is my optimized version, does it react, does it pass the same test suite as my non-optimized version? And the only thing where you are sure that, where you want to prove that it's equal is via the interface. And this is why we generally do not write tests on the contract level itself against the contract, but write the tests against the interfaces. And here we, for example, we see this is the Scribe test for the interface, not for the specific version. And this allows us, if we want to write a Huff version of Scribe in the future, or a Yule version, or a Viper version, we don't have to adjust the test suite. I mean, you have to, of course, adjust the test suite for some edge cases and for lower level testing. But this test suite must pass. And if you come up with a Hub version and you pass this test suite, we are fine in saying, okay, after one more security audit, we will deploy the Hub version, because we have proven for every use case that we could think of, for every functionality, that these two programs are equivalent. And then we do not have the normal setup function. We override the setup function and you give us some address. We we assume it's this interface of Scribe, and from there on we start with all our normal testing. Like we use here a lot of fast testing. We use a lot of normal testing as well, because fast testing seems to have a lot of problems with gas optimizations, and it's kind of not so nice in the CI when you check the gas snapshots. So we basically have fast tests for everything. We have differential fast tests for most of the stuff. We also, for example, in the elliptic curve computations. We use differential fuzz test against Foundry's implementation, for example, of how to get from a private key to an address. We do the same here. We have the private key, we write a public key and that to an address, and we check whether both of that is equal. We also check for optimizations that we implemented. So we have this, if you have two coordinates, so let's say you have x and you have y, and you want to prove, you want to ask, is x and y 0? So basically, is this the 0 point? Then of course, the normal way you program this as a developer is just saying, okay, if x is 0 and y is 0, then yes, that's a 0 point. At some point, we started optimizing it because you can also just say this. This is a logical OR. So we check if this bit string basically and this bit string, and we check each bit against each other. And it's only 0 if both of them are 0. And we see that we saved one operation. This is like 3 or 5 gas. This is not really something that you should do in the beginning while you develop the project. It should be at a later stage, I think. And if you implement this, then make sure that you test against your old implementation. Yeah, to not, like, it would be a shame if you develop a project for a long time and then you get hacked because you implemented one bit optimization too much or something like this. This is just too sad. And then we have, like, we also check a lot of times for constant or for the gas usage in general. There you have to be careful. This via IR pipeline generally sometimes changes stuff. For example, here it's actually not constant. It uses 3 times less on the second run because there's some optimization. And we also use vector test cases. So we have here in vectors, we have a big list of public keys, P and Q. And if you add these two public keys together, this should be the result. I stole all of this list from Paul Miller, who has this great noble curves project, like basically elliptic curve in JavaScript. And this kind of tests are like, use as much testing as you can. Do not only use forge testing, fuzz testing or something. Write your own script in different languages and test whether your script is passing your solidity test. And if you have this, if you want to use this kind of things, you most of the time need to have some kind of, in this case, JavaScript, some kind of small file to read this data and ABI encode it so that you can read it into Forge via FFI. And this allows, this basically allows you to have vector-based testing. One thing I think we should take care of in the future is EVM compatibility is is bullshit most of the time. Really do not depend on this. Make sure that you test it yourself. There were a lot of problems already, and there will just be more problems if every chain decides when to update to new hard forks whenever they want. And it will be a pain in the ass to set the EVM version every time correctly and stuff. So write as many tests about your EVM framework itself, EVM environment, and run it against a specific chain to check, okay, is this assumption still correct? For example, here we have the very simple assumption that a call data load, if you load call data which does not exist, it should not revert. This is very important for this challenging again. Otherwise, the challenge may revert if you provide not enough call data. And it's very important that if you load call data which does not exist, it must return 0 and not revert. And we have here similar tests, mostly what easily we cover then, where we just check our general EVM environment. Some invariant testing, which is, I think, like for invariant testing, definitely check out Horsefac's article. It's also linked here. It's by far the best article I found about it. And he has, he's testing the WE's implementation and has a lot of nice features and modifiers there that he presented to make everything there easier to handle. And remember that for this testing and stuff, don't gas optimize. optimize for readability, optimize for simplicity, but don't optimize for any gas optimization except your vectorized, and your test suite should run in a second or something like this. And yeah, I think this is from me all that's to say, basically. I mean, I could go into more detail of everything, but yeah, I think if there are like no more questions, I would just invite everyone to check out the repository, write to me on Twitter or Discord, or join into our Chronicles Discord and ask questions. If you have suggestions how to optimize stuff, we definitely have an open ear for that. And please figure out, like, try out with the Schnorr signature stuff, because yeah, it gives you more security than multi ECDSA signatures, because you don't have this linear call data and runtime load. And it's a lot cheaper than BLS signatures, even with the precompiles, which are coming at some point for this new BLS curve. So check out Schnorr signatures. It may be a new way of how to do multi-signatures in EVM.
Nice, nice. Very cool stuff, Pascal. Thanks for a great presentation. And yeah, probably the main innovation in the repository is the Schnorr multi-sig stuff, which is really exciting. One last question regarding the optimistic oracle, just to check my understanding. So currently there is like a challenge period of 1 hour, right?
This is just like during the deployment, we always set all the data, like set everything. We also have a bar initially of 2. This is of course not be used in real time in the real system. We generally have the approach deploy a contract and afterwards configure every single step.
Okay.
Yeah, to make the deployment also, because on some chains we may want to have a different optimal challenge than on others, and to generally make everything more. It needs to be a step to change this value. You don't have in mind was it an hour or not. So we configure everything as soon as we deploy it.
Okay, let's say it's X minutes, okay? If I'm a protocol and I need the price, I would always get the last finalized one, right? Which would be like X minutes ago, correct?
Yeah.
Okay.
You do not have access to unfinalized data. It's private, and we were thinking about whether we should allow projects, because theoretically you could figure out already whether it's finalized or not, right? Because you could simulate the OP challenge function on your own, see that it passes, so you verified everything, and then say, okay, hey, the value is fine. I use it already, even though you don't give any promises about this. But we decided against this because we put as much as focus on verifiability as possible, and you should not trust us, and we don't trust you to, like, the consumer, to use the oracle in a way that it's like we want to make everything as simple and as secure as possible, and we do not want to give any like going around the corner and maybe like destroying your own protocol because you misunderstood something. And if you really think this 1 hour, let's assume we use 1 hour, would be too long, you can always challenge directly, and this finalizes the data as well.
Okay, interesting.
So this is, like, for example, also for front running, something important. If you have front running problems, but only during the deployment, for example, or during one specific moment, you can use flashbots or any private mempool. Optimistically poke and challenge, or just poke directly one transaction before your transaction where you would create front runnability, and make sure that the oracle updates exactly when you want to make sure that you're not vulnerable.
Okay, makes sense. Awesome. Then, Pascal, thanks for taking the time. This was a really great presentation, really interesting project. I'm gonna look into it more, because we're looking at a Oracle design for Dyad as well. Great thing, it has the Chainlink interface, because we're using Chainlink, so we could just change that, which is great.
Yeah, we thought so.
Thanks
Cool.
again. The best place to find you is Twitter, I guess, right?
Twitter, yeah, merkleplant_ETH.
Okay, so I'm gonna link merkleplant's Twitter in the description below. I also put in the repo, the website, all the good stuff. So yeah, thanks again, man, and see you on the next one.
Yeah,
Bye
nice.
bye.
Thanks.
Bye bye bye.